Good afternoon. How are you everyone? In today's research seminar, which is related to statistical associating fluid theory, simplified activity coefficient for fast phase equilibrium calculations, and I am engineer S. Kamil, Masters in Chemical Engineering. I have joined on 1st September 2021, working under the supervision of Professor Dr. Violet from Department of Chemical Engineering and Interdisciplinary Research Center for Refining and Advanced Chemicals, KFUPM. So the contents of today's presentation are: first is introduction to the area of research. What is the area of research in which we are working, and the motivation for selection of this area. And then I will be sharing the abstract of my thesis, which is my master's thesis, and then I will share the methodology or the theory which we are adopting, and then I will be sharing our research results with you. We have conclusions, way forward, future plans, and the last but not least is the acknowledgements to our professors. So basically, physics has different branches like optics, cosmology, photonics, electromagnetism, thermodynamics. So this thermodynamics is actually from the branch of physics, and then we have two different main branches of thermodynamics. First is the classical thermodynamics, and then we have the statistical thermodynamics, or also the stat dynamics. So there are different approaches used in both kind of thermodynamics. Like in the classical thermodynamics, we are looking macroscopically into the systems. Like we are measuring the measurable quantities like density, temperature, pressure. Any other thing, Magaji or Khairul? Like in the macroscopic classical systems, what properties we are using and we are measuring? Like we can measure the density, temperature, pressure, or the composition or the viscosity of the system. But in the microscopic approach, we are looking microscopically into the system. Like we are looking at the structure of the molecules, we are looking at the diameter, the kind of interactions, the attractive or repulsive forces between the molecules. So this is the microscopic approach which we are using in our area of research. So why we are working in this research area? Because there is a demand for strong theoretical understanding. Like in the classical approach, we don't have the physical understanding what's happening into the system. We just have some empirical or semi-empirical results, we are fitting the data to it. So we need some theoretical understanding, so we need to look at into the molecules, how they are interacting to each other, what kind of forces they have and why they have these forces, kind of dipole-dipole interaction, some polar molecules, some non-polar molecules. Then because of this demand, we need to estimate the behavior of industrially relevant systems. Like what can be a perfectly industrially relevant system which can be modeled? Like anyone working in industry? Like we have methane gas. We have some methane gas in equilibrium with some other gas like ethylene. So there are different conditions of temperature and pressure. Or we have a distillation unit. We can have a system in that. Like one famous system is acetone plus chloroform. So you are separating the acetone and chloroform in a distillation column. So you need to know what's happening into the system microscopically. So if you have some thermodynamic model or some simulation data, it will reduce your number of experiments. Like you don't have any theoretical understanding or you don't have a model. You need to do 200 experiments for each kind of condition you want to operate. But if you have some thermodynamic model or some simulation data, you just get the simulation data or use the thermodynamic model and validate the experimental results over that. So it will just reduce the efforts or the cost involved in that process. So this is the motivation for selection of this research area. Also, the reported data is used in sizing of the equipment. So if you want to just size some distillation column like acetone plus chloroform, so you need to know what should be the pressure in the system. Like at the temperature of 500 Kelvin, what will be the pressure? So the thermodynamic model will tell you the pressure. So according to that pressure, that temperature, you can size the equipment for, like, if there is very high temperature, we can we know that there will be some heat of mixing in the system. So there is very high temperature. So what should be the material of construction of the column? It should be some ceramic, some steel, some alloy. So this data will help us in that. So in the abstract of my thesis, it's related to molecular theory and simulation for associative flows. So the activity coefficients derived from perturbation theory based equation of state. So actually the perturbation theory based equation of states, they have the physical understanding, not like the cubics. The cubics like RK, SRK, van der Waals, they don't tell us what's happening into the system. But the perturbation theory, they have hard chain term, association term, polar term, and dispersion term. So this work will also be applied to enhance oil recovery from the wells by injecting CO2. So the PGSAT simplified activity coefficient thermodynamic model is used for estimating the vapor liquid equilibrium, which is actually the TP phase diagram. So at the last, I will be doing the comparison of estimated phase equilibrium results with that of from SAT, SAC and SAT AC. So in the methodology or theory, we have the polar PGSAT equation of state, which is the residual Helmholtz energy is equal to the Helmholtz energy by the hard chain term, dispersion term, association and the polar term. So if you want to know how these terms are calculated, you can just open the reference on the next slide and you can easily calculate these terms. And regarding the activity coefficient from the UNIVAC, which is the universal quasi-chemical thermodynamic model. This is the length gamma is the activity coefficient equal to combinatorial plus residual activity coefficient, and the rest is the main equation which we use. So these are the pure component molecular parameters. Like we have the diameter of the segment or the molecular diameter. So we should know what is the diameter of molecule. We should know what is the association energy, with how much energy they are colliding with each other or they are combined. Then we should know the association volume. Then we should know the dipole moment. So we are using, or also we need to know the fraction of polar segments. Like if we have a system of simple alkenes, will it have some polar segments? Like we have some simple alkenes. Lahmadi brother. Will we have some polar segments in simple alkenes? Like methane, ethylene?
Depends.
It depends. But mostly because there is not a lot of electronegatividity difference. For those systems, there will be not a lot of polar segments. But for example, if we have acetone, like some fluorine, like hydrofluoroolefins, then because there is a lot of electronegativity difference, the electrons will be pulled towards one end, which is more electronegative. So those systems will have more dipole moments or more fraction of polar segments. So these are the solvation parameters. Solvation is related to the interaction of the molecules within a liquid. So this is in our research results. This is one of our results just published in Industrial Engineering and Chemistry Research, which is related to phase equilibrium of cross-associating mixtures using association theory-based equation of state. And the funding was provided by this body and by our professor and some other professor. So the results of this research work are, let's say we are estimating the phase behavior of acetone plus chloroform binary mixture at a temperature of 300 Kelvin. So we can see that these circular points are experimental data points, right? Mustafa? Circular points are experimental data points, and these dashed lines are from the UNIVAC model, and the solid lines are from the polar PGSAT. So you can see that. Let's leave this PXY diagram for some time. This is the activity coefficient diagram, and in the excess enthalpy, which is related to the heat of mixing. Like if we mix two different liquids, there will be some heat evolved or generated or absorbed. So this is the heat of mixing. If we mix one acetone with a chloroform, then how much the heat will be liberated per mole. So you can see that polar PGSAT accurately estimates the heat of mixing. So in comparison, if we don't consider the solvation. We say, okay, in the acetone and chloroform mixtures, they don't interact with each other. They have no kind of attractions or repulsions for each other without solvation. Like here we have no solvation. So in these results, we can see that polar PCSAT is not even able to actually capture the behavior of the system, like how much energy will be liberated. So this is a strong evidence that there is solvation effect in our system. Solvation parameters: cross association energy and cross association volume. This is another system of MTG plus chloroform. You can see that there is some azeotrope formation in this region. But if we are using the Univac model, which is the excess Gibbs free energy model, which do not have the physical basis for it, but it's mostly reliant on the experimental data, and we extract the Gibbs free energy for it. But on the other end, we have the polar PCSAT model. It is accurately estimating the azeotrope. You can see this. You can observe. So the azeotrope is estimated with great accuracy as compared to the other model. Also, in this activity coefficient model, you can see that if we use radius or Univac model, thermodynamic model, so these data points are more close to the solid line, which is our polar PCSAT. So our thermodynamic model. Similar goes with the pH diagram and activity coefficient, indexes enthalpy for the diethyl and chloroform mixture. Especially in this region, you can see that the excess enthalpy is estimated with greater accuracy. So, in the conclusions, the polar PCSAT is giving better results than Univac and reduced activity coefficients for solvating mixtures. However, the polar PCSAT just requires 2 parameters in comparison to 4 parameters in Univac. So the traditional excess Gibbs free energy models are unable to better predict the composition dependence of activity coefficient. So the predictive capability of polar PCSAT is better for estimating activity coefficients at infinite dilution. Because you can see that here in the infinite dilution region, when the MTP is very less, like we are doing some distillation, so there is very less MTP in chloroform. So if we use the Univac model, like in this one here, the Univac is giving us the false activity coefficient. So if we use that activity coefficient for calculating the pressure, like we are using any Raoult's law or anything, we are using this activity quotient value. This is faulty, like this is faulty. But this activity quotient value is more accurate. So we should not use those values. Yes. The proper estimation of interactions of hydrogen bonding distribution has allowed to fit excess enthalpy. So in the way forward for the future plans, the fast-paced intelligent calculations will be done using SAP-SAC and SAP-AC thermodynamic models for the refrigerants plus U volume. Because in the refrigerant systems we have the refrigerant which can be HFO, hydrofluoroolefin, and kind of U volume. So we can measure the solubility of that refrigerant into the U volume. So using our thermodynamic model, we will apply this to the refrigerant systems now. The obtained results will be leading to larger applications because in industry the SAP-SAC model can be used for thermodynamic properties estimation. So property prediction of polymers is another part which can be done using the SAP-SAC, but this is not related to all. So finally, the last but not least is the acknowledgements to Professor Dr. Vaisar for Dr. Naim Al-Sefi, Chairman Dr. Hassan Mohammad Baki, Dr. Ahmad Zahir, Dr. Sheikh Abdul Razak, and Dr. Kamal Mohammad for helping in some Aspen Plus software simulation, and the lecturers Mr. Farooq Shahzad and Mr. Sadiq Khalaf. Thank you for listening. Now,